Okay, so today we're going to talk about magnetism. Now, this will probably be something you're familiar with in terms of the word. You've dealt with magnets your whole life from elementary up until now, but we're going to talk about them in a little more detail, kind of give you some behind the scenes understanding of what magnets actually are and how they relate to electricity. So, magnetism is the properties and interactions of magnets. So, that word just is talking about the idea of what magnets do. And also, I'll say that anything in green, I'd like for you guys to write down, and anything in yellow, you can just read for today, okay? So anything in green, again, that's what you write. Anything in yellow, that is what you just read. So also, the earliest magnets were found naturally in the mineral magnetite, which is abundant in the rock type, I think it's idostone. These magnets were used by the ancient people as compasses to guide sailing vessels. Magnets, they produce magnetic forces and have magnetic field lines. And here's some examples so you can see that, and we'll talk about this on the next slide, but there's two sides of every magnet, and they create these field lines because of the forces that are trying to go towards one another. Remember, opposite charges attract, so you can see how the lines are trying to connect to the other side of this magnet. Just like here with these fine pieces here, they're trying to go to the other side because opposites attract. So magnets in general have two ends or poles. They're called north and south poles, and at the poles of a magnet, the magnetic field lines are closer together. So as you can see here, they're really close, and as they go further apart, as they go further away, they get farther apart. And it says right here again, magnets are closest together at magnets poles. Okay, right here as well, you can see how they're closer, and as you go further away, they get further apart. Unlike poles of magnets attract each other, and like poles of magnets repel. So this is kind of the same idea as charges. Like charges, they repel, and opposite charges attract. So unlike or opposite charges or opposite poles of magnets, they attract each other. As you can see, if they didn't, you wouldn't see the lines trying to go towards the other side. You would see them going away, right, in the opposite direction. But since it does, it makes this almost like this circular field encompasses around the magnets. So actually, Earth is like a giant magnet. The nickel iron core of the Earth gives the Earth a magnetic field much like a bar magnet. So as you can see here, the iron core, which obviously it's not this big pink rectangle, but there's a big inner core of the Earth that is made up of nickel, which is a natural metal. A natural magnet, and has these two different polar sides to one another, south and the north pole. So with that, the Earth in itself creates a giant magnetic field, and that's what we use for compasses. So what are magnetic domains? Well, magnetic substances like iron, cobalt, and nickel, and those are the three big ones. So on a quiz, I've asked you what are the three elements that are natural magnets. You would say iron, cobalt, and nickel. These are composed of small areas where the groups of atoms are aligned like the poles of a magnet. So the atom itself is aligned like a magnet. And these regions are called domains. So all the domains, and I'm going to go ahead and click here, all the domains of a magnetic substance tend to align themselves in the same direction when placed in a magnetic field. So these domains are typically composed of billions of atoms. So this is not like we're just dealing with a couple. We're dealing with billions upon billions. And you can see here, a normal iron nail is made up of billions of domains that are arranged randomly, so that they look something like that. But you see how they've got their poles already. But whenever you put that iron nail in contact with something, with a magnet, the domains will align themselves along the magnetic field lines. So if the magnet has a north and south, right, you'll see how they're flipped. You see how this is north, and then all the ones are south on top, and all the ones that are south on the bottom are north on the bottom, because again, opposite poles or opposite charges attract, right? So I told you at the beginning of this that electricity and magnetism are related, but how exactly are they related? So when an electric current passes through a wire, which we've talked about that the wire is the way the current is allowed to pass through, a magnetic field is naturally formed. So, and it says it here again, a magnetic field forms around the wire, and it's represented in these little blue lines. And the direction of the magnetic field depends on the direction of the current in the wire. So as you can see, if it's flowing in a right direction, it's going to be going counterclockwise. If it's going in a left direction, it's going clockwise. Just from this picture. So, what is an electromagnet? When an electric current is passed through a coil of wire wrapped around a metal core, and I'll show you a picture here in just a second, a very strong magnetic field is produced. This is called an electromagnet. So this is in theory what it's talking about when it says when current is passed through a coil, which a coil is just a wire that's wrapped, okay, that is wrapped around a metal core, which is a magnet, okay, a very strong magnetic field is produced. This is called an electromagnet. So when you pass electrons, you can't just have a core. You can't just have a coil of wire that runs through. You have to actually have current that's passing through electron flow. But when you have that and you have it wrapped around this magnet, you do get a very strong magnetic field. You can see that here. So galvanometer is an electromagnet that interacts with a permanent magnet, and I'm going to show you a picture here again. So the stronger the current passing through the electromagnet, the more it interacts with the permanent magnet. So here's your electromagnet, and here's your permanent one. Okay, just to give it, see, it says right here, includes a permanent magnet, electromagnet that rotates against the spring in a scale that gives a measure of the current. So when that current is going through this wire here, you can read it on this meter. It's just a way to detect how strong the current is. So the greater the current passing through the wires, the stronger the galvanometer interacts with the permanent magnet. So real quickly, and this is just, and we're going to talk about this in a real general sense, is an electric motor. An electric motor is a device which changes the electrical energy into mechanical energy, and we use these all the time. You may not have ever seen one set up like this, but this is basically how an electric motor is. It's a power supply, like a battery, a permanent magnet, which would be something like this, and an electromagnetic magnet that can rotate. So if I showed you a picture, I would ask you what this is, and you would be able to tell me it's an electric motor because of this power source, permanent magnet, and the electromagnet right here. So, and how does it work? Well, let's just follow the steps. So a battery causes electric current to flow through the coil of the electromagnet. Okay, so there the coil goes, and here's the electromagnet right here. Unlike poles, the two magnets attract each other, and like poles repel. This causes the coil to rotate until the opposite poles are next to each other. So you see how there's a north and a south. So they'll rotate until they get to the south-north, north-south. See, they're opposites for these two different magnets. And so then the current in the coils, if the current in the coils is switched, the direction of the coil's magnetic field also switches. And then the coil is repelled and attracted once again to the poles of the permanent magnet, and the coil rotates until it is aligned with the permanent magnetic field. So it just keeps rotating pretty much is all we need to know. So I guess there should be a sentence here, but it says electromagnetic induction. This is moving a loop of wire through a magnetic field that produces an electric current. An example of this would be a generator. This is used to convert mechanical energy into electrical energy by electromagnetic induction. And there's that word. So the top of this slide should be electromagnetic induction. Okay, so you can pretty much what this is saying in a very basic sense is that you can use mechanical energy into converting into an electrical energy. We know what generators are. Generators are the forces behind all power plants that use that we use to create electricity for. Oh, there it is right there. Okay, and the last thing, we'll go click through this, is now there's two different types of currents, and I threw this in here at the end just simply because it's better to talk about it once we've talked about magnets. So let's go through this quickly here. A direct current is the electrical current which comes from a battery, which supplies a constant flow of electricity in one direction. So pretty much direct current, one direction. Okay, it's not going to go in any other direction. So if you have a battery supplying this, then you will be flowing electrons in one direction. Okay, which is typically how most things are ran, just simple circuits. Okay. Also, though, however, there's alternating current, which is electrical current. It comes from a generator, and as you've seen before, it has something to do with the electromagnet that is rotated in a permanent magnet in the direction of the current. So, and that current alternates once for every revolution. So it'll turn clockwise, and it'll turn counterclockwise, turn clockwise, turn counterclockwise. So it'll rotate. And so that one, since that rotation is there, we call that alternating current. Okay, and that's all about magnets. Thank you guys.